And today I'm going to talk about some of the work my group has been doing on end-user customization for mobile devices. If time permits, at the very end, I'll say a couple of words about some other projects that we have going on. In general, I lead the mobile computing research group in our department. All right. So this is probably old hat for all of you, but I mean, just I guess bear with me. As we all know, mobile devices are challenging, and they present a very challenging environment for people interested in browsing the web, which will be the focus of this talk. I mean, there are many reasons for this. Among others, the fact that there is actually significant variability between the affordances provided by mobile devices, and I have an example here where you can see different devices with completely different display sizes. Energy is also a very significant issue in mobile environments because, well, roughly you are limited by the size of the battery that you're willing to carry around. Bandwidth is an issue. It has been getting better. I mean, we've been getting better wide area connectivity, but still the kind of bandwidths and latencies that you see over a 3G connection are significantly lower than what you get over, let's say, a residential DSL connection that is, half decent. And worse, for many people, bandwidth is still not free. So either they have a plan that has a hard cap, or they pay X amount of dollars per megabyte. And what all this boils down to is to a fact that we actually have to adapt web content to make browsing on mobile devices a more enjoyable experience for the mobile device, for the mobile user, I'm sorry. And there are different ways in which one can adapt content. The one that is used the most today is basically manual adaptation. So you actually pay someone to maintain multiple versions of your content for different devices. So you have a desktop version, you have a mobile version. And this is fine, it works, but it has a very high human cost and it involves a significant investment. An alternative is to rely on some kind of automatic adaptation, some kind of automatic transcoder that adapts the data for you. But the problem is that this automatic transcoders tend to be less than perfect because they have a very limited understanding of the data that they're trying to adapt, especially if I'm thinking of applying a transcoder to pretty much all data that may come from the web. So an example that we can provide is, if you're, let's say, browsing the web because you want to buy a mobile phone, well, this low fidelity version of a Sony iBodog is probably fine because you don't care about buying iBodogs. But if you get a similar fidelity version for a phone, this might not be sufficient because you may actually want to know more about this phone. So the issue is that we want automatic adaptation, but at the same time, we want this adaptation to be tailored to what the user is going to do with that content. So we want smart automatic adaptation. So today I'm going to describe two projects that attempt to do what we call end-user customization. They basically put the user in the driver's seat and say, well, the user knows what they want, so let's them adapt the content, but that basically just pushes the buck to the user. So now actually all the effort has to be put in by the user. So what we're going to see is techniques that actually try to limit the amount of effort that the user has to put in, so that potentially I adapt the content only once, and then I can actually leverage the adaptation over a long period of time. And that is what the first project, PageTailor, is all about. And then I'm going to talk about the second project that we call Eureka, where what we're trying to do is we're trying to leverage the effort put in by some people in the community to benefit other people in the community. Specifically, if we have maybe a subset of people adapt the content, then maybe a larger group can actually take advantage of whatever adaptations they make. So let's start with PageTailor and with a very specific example. Let's assume that you happen to be avid BBC news readers. This is a screenshot taken about a year ago of the BBC main website. This is how it looks on a desktop, and it's, that particular layout is optimized for the desktop, and it works very well. The problem is that if you actually want to read this page using a mobile device, and just as an illustration, I have a PDA here, but the form factor, I guess, of this PDA is very similar to what you would get with the current, an iPhone or an Android phone, give or take. So the problem is that it has a display that is much smaller, and only a small portion of the page fits in there. So in this case, let's assume that the user is interested in the top stories that occupy that portion of the page, plus some popular stories that are on a different side of the page. So what they'll have to do is they'll have to do a lot of scrolling. And with some of the newer browsers, they'll have also to do zooming in and zooming out. And yes, this works, but it gets in the way of fluid interaction. It's extra effort that you have to do to accomplish your task, which is basically you want to read those things. So what PageTailor is a program that runs on top of your browser that lets you customize on the device pages that you download. So what it does, it specifically lets you remove elements. So if, let's say, if I'm only interested in those those tidbits of the page, I can remove all the other portions I don't care about. I can actually move them around, I can relocate them, and I can actually resize them so that it's easy to read. What's interesting is that PageTailor actually records these customizations and reapplies them on future visits to the same page, even as the page changes, even as the content changes, because if you go to the you go to the CBC page, you show up there 20 minutes later, there'll be new stories. So even as the content changes, it will reapply these customizations so that you get it, you get the new version of the page in the shape that you want it. And more so, it will actually try to reapply the customization to other pages in the same site. So an example of that, if you customize, a specific page that shows one news item, if you then go to a different news item, it will reapply your customization so that you get them automatically. So some advantages: it's a very easy to use tool. Basically, you get what you see is what you get interface. It's very expressive in the sense that it supports quite a few different adaptations. Right now, we have it, a prototype that's an extension of the Minimo web browser. It's all written in JavaScript, and it's all client-based. So it all runs on the mobile device. You don't need the support of a proxy. Although if you do have a proxy, then the proxy can potentially do some of these changes and save, let's say, energy on the device by not downloading elements that you're going to crop in any case. So some of the advantages of this approach, well, basically it puts the user on the driving seat, so they really get to modify the page any way they want it. And it's also good for the provider of the content because they don't have to do anything. The obvious question is, well, why would people do this, or when does it make sense? As it turns out, actually customizing the page takes more time than just taking the page as is and performing your task. Because you have to do even more scrolling, and you have to tell it, that you want to hide certain elements and resize other elements. So the total time, if I'm looking at the time to complete a task, actually goes up, because now you're first customizing and then you're performing your task. So if you're going to use this content only once, this doesn't make too much sense. Now, for content that you're going to be coming back to over and over, or if we can reuse a customization across similar content, then it makes sense. In other words, if this is a page like a portal that you're going to be checking every morning, then it's actually okay to maybe spend, the first time that you go to this page, you spend 5 minutes customizing it, because you're going to reap the benefits of your effort over a long period of time. And the same goes if, let's say, I have to customize a small portion of the website. If by customizing a small portion of the website, I then get to basically browse, the whole website, then maybe it's worth me spending that effort in a few pages. So you may ask, well, why does this work? Because you're basically saying that you're going to reapply customization as the content underneath changes. Well, the reason why it works is that because most websites basically use a very small number of layouts. And these layouts typically remain unchanged over long periods of time. And by that I mean potentially months, in some occasions even years. And why is this? Well, you want to present a consistent interface to the user. If the site is consistent, it's easier to use, it makes possible branding, and it's also cost effective, which is good for us. So how does it work? Well, when the browser renders a page, it also creates a DOM representation of that page, and we use that to record the modification. So for instance, in this very simple schematics of a page, we have a paragraph and an image, and let's say the user, okay. Let's say the user changes the size of an image. What we do is we actually record that change, and we record the path across the DOM where that change was done. So we record that, in fact, this is the image that is in a given position of the body. And why is this? Because we want to be able to reapply the modification even if the content underneath changes a bit. How does it work? Well, next time you go to the same page, we download the page, we render, we execute all the JavaScript that might be in that page, and after that, PageTailor executes. And what it does, it basically tries to look for these paths of the content that you modified. And if it figures out that the path is still there, it then applies the modification. This works, but more often than not, there are actually small changes to the page that make the naive technique fail. And an example of that is, for instance, you have your page, and let's say that it was slightly modified. There is an advertisement that was added somewhere on the page. Most of the page is unchanged, and in fact, the user's customization is still valid. But if we just try to do, I guess, a topological comparison of the two DOM trees, we'll find out that they are different. So instead, what we do is we optimize our search a bit, so that if we don't find, in this particular case, this is, let's say, the DOM that results for the modified page. If we don't find the path, the original path in the tree, what we do is we do a search, and we basically look for nearby portions of the page of the DOM tree, trying to find out that particular part that you modified. The problem with that is that it can basically result in false positives. So to try to minimize the amount of false positives, we take into account context. So in this example, if you modify the image, we also remember that that image was, let's say, inside a specific div or after a given table. And we use that context to try to rule out these false positives. In this example, we would find the image and we would increase its size. All right, so question, does it work in practice? So we actually performed an evaluation. We did two kinds of evaluations, what we call a quantitative and a qualitative evaluation. And we answer a few questions. First of all, does it work on a PDA? And the answer is yes. Two, can normal users actually take advantage to this to modify content? And the answer is yeah, they're willing to do that. How long does it take to modify a page? It really depends on the complexity of the page. Some of the experiments we played with, these were fairly sophisticated pages, and even a very sophisticated page, it takes you about 10 minutes to customize it. And the other question we ask is, okay, well, given that you're going to have to spend 10 minutes customizing the page, well, what kind of payback or payoff you would expect to see for that investment? And what most people told us is that as long as the page remains, as long as their customizations remain useful for about a month, they will be willing to spend 10 minutes customizing. So the question that we then obviously try to answer is, well, is this actually the case for common pages? Do they customizations, do user-generated customizations remain relevant for at least a month? So we performed two studies, what we call a longevity study that basically tried to answer that question, and also a coverage study, which was looking at a slightly different question, which is, well, if I modify, one instance of, a couple of pages in a website, can I reapply those modifications to other pages, to other similar pages, and roughly what kind of coverage of that website I get by modifying a small number of pages. So to answer first the longevity experiment, what we did is we downloaded popular pages from Amazon, BBC, eBay, and MSN. And we actually went to a web archive, and we got 16, we basically went as far back as 16 months. And we got the historical, it's also a trace of each of these pages, as it changed over 16 months. We then selected, participants, basically 4 for each of those pages. And we gave them the page as it showed up, in day 1, basically 6 months in the past. And we told them, go ahead and change it any way you want. So adapt it any way you want, any way you see fit. We then recorded that adaptation. So the users actually adapted it on the mobile device. But to evaluate the longevity, what we did is we left, we told them, okay, we're not going to do the evaluation on the mobile device. Leave the mobile device. We moved them to a different setting where they had 2 monitors in front of them. The monitor on the left showed 2 windows. It showed on the left side, basically here, what we have is the page before their adaptations. On this side, we have the page after it was adapted. And this is basically on the day they performed the experiment. On the second monitor, what we did is we basically showed them how the page changed over time. So we basically, jumped 1 week, in the future. And we said, this is what the page looks like. And we reapplied the modifications automatically to, the version of that page 1 week into the future. And we then did that for, 2 weeks, a month, 2 months, 3 months, and so on. And what the users were asked were to answer for each time we showed them, a new version of the page, they had to answer 2 questions. They had to answer, first of all, whether their customizations were still desirable. Okay? Whether, given the uncustomized version of the page, whether they would still like the customization to be applied. And if that was in fact the case, whether the customization was actually properly applied. And let me just present results for one of these sites. The other ones are also similar. And if you're interested, at the end of the talk, I'll have a URL from where you can download our paper that has much more, detailed results. So what we saw is that this is actually the page for the BBC. What we see is on the x-axis we have time. So this is basically the day the customization was performed, 5 days after the fact, 83 days after the fact, 249, and 500 days after the original customization was performed. And on the y-axis we have people. So basically the day the customization was performed, all 4 participants were happy with it. I mean, after all, they performed the customization. What's interesting is, up to even 500 days after the fact, they still think that the customizations are desirable. This means that basically the layout of the page hasn't changed that much. Now the question is, well, given that the customizations are desirable, let's say up to 249 days, after they are done, can we actually take advantage of this? And what's interesting is that for 75% of our users, we can actually. For one of the users, actually, some of their customizations were not properly applied. But for 3 of the 4, in fact, all the customizations they performed were properly applied up to 1.5 years, after, after the original customization. So that's actually great, because it means that, users are able to put some effort to customize their page, and then they can actually take advantage of that effort over a very long period of time. And for all our sites, this was the case for at least a month. So the second experiment, oh, by the way, if anyone has a question and wants to interrupt me, please go ahead and do so. You don't have to wait till the end, right? So, just raise your hand or, shoot. Anyway, so the second experiment, we wanted to figure out whether, what how many pages in a website I have to customize to pretty much get access to the whole website. And what we did is we took 4 other popular websites and 20 participants, and we asked basically 5 participants for each website, and we asked them to customize 2 pages from each of these websites. So if you think about it, it's basically sort of like a portal page, and then I guess a news item page, or in the case of Flickr, a specific page for an album, and then a page for a picture. And once they customized that one page, what we did is we downloaded a very large number of pages from that same website, and we reapplied the customizations, and we actually went and we checked them, and we saw whether the customizations were properly applied. And these are results for Amazon. So in this case, what we did is we gave them, we asked them to customize a page for a CD and a CD listing. And we then applied the same customizations over a large number of CD, other CD pages and other CD listings. And what you can see is that, in fact, the customizations are reliably applied, across similar pages, which is great. Because what this means is that when you go to Amazon, first time you go to Amazon, you have to customize, the first time you go through Amazon, you have to customize pretty much every single page. But later on, as you keep visiting other pieces of the Amazon site, the customizations are automatically applied for you. So the amount or the number of pages that you have to customize in a website is limited. It's, you only have to customize very few pages, and you get to see the whole site. So that's actually very good. Some practical considerations. The way I've presented it so far, it seems as if the users have to do the customizations all at once. In fact, actually, that's not the case. And the way we see people using PageTailor is in sort of an incremental fashion, where they go to the page, they do some customizations, they accomplish their task, then they go away, they come back to the page the following day. They figure out that they want to do a bit more customizations and so on. And PageTailor supports this. So the 10 minutes that I mentioned that people have to spend customizing the page doesn't, it's not something that you have to pay up front. You can, customize as little as or as much as you want. Another technique that we've explored is whether we can actually have, if we identify users that are similar, whether they can share templates. So if your buddy customized the page in one way, maybe you don't have to start from scratch. And in fact, actually, the second part of this talk will describe much more research into that direction. All right. So just to summarize this first part of the talk, I presented an approach where we let users customize on their device, and the customizations are reusable. The customizations, are basically, they reflect the user interests. And they can be reapplied on the same content or across similar content on the same page. And this works because the structure of the websites tends to remain stable, even if the content changes all the time. We actually have a prototype of PageTailor, which is available for download on that URL. Alternatively, you can go to my homepage, which, last slide of this presentation will have the URL for my homepage, and there is a link to all my projects, and one of them is PageTailor, and you can get the prototype from there. Right now, it only runs on Firefox, or Minimo, which is really the mobile version of Firefox. All right. So we are very optimistic about the results we've been getting with PageTailor. We think it's a very useful tool. And it's great that you can reuse the customizations that you yourself made. But at the same time, it still requires significant effort. So the question we asked was, well, can we leverage this effort across users? So Yes, it's true, different users may want different things, but in reality there is only a limited number of ways in which people, browse content, and it's likely that you're not the only person in the world that wants the content in a specific way. So can we take advantage then of the fact that maybe somebody else has already customized the content so that you don't have to start from scratch? And that's exactly what the second part of this talk will address. We have a technique we call Eureka, which stands for Usage-Aware Interactive Content Adaptation, that is based on this idea of leveraging customizations across people. It works in the following way. Basically, the system provides content with a random adaptation if it doesn't have any history, and then lets users change it. The system now learns from the user's modifications and builds a history, so that next time when somebody asks for the same content, the adaptation is actually based on this history of modifications made by other people that have interacted with the content in the past. Now, we believe that Eureka can be applied to a wide set of adaptations. Page layout is one of them. But for simplicity, today all the examples that I'm going to provide are actually based on image fidelity. Why image fidelity? Because it was actually just easier to build experiments so that we can actually evaluate, get hard numbers about how good this technique was. But we believe it can be extended to layout. So let me give you a very simple example of how this works. Let's assume that we have a mobile device that accesses the internet over some type of connection. The user downloads a page that has an image embedded in it. It is this particular image. The full fidelity version of the image is 40 kilobytes. So instead of accessing the website directly, the user actually goes through a transcoding proxy. The transcoding proxy gets the image, and this is the first time it has ever served the image. We don't have any history for it. So it applies predefined adaptation rule that basically transcode the image into lower fidelity representation, which in this case is about 1/4 the size, and serves the user that low fidelity representation. Well, if it happens that this particular user is actually a fan of, is a beer fan and really, is not happy with a low fidelity representation of, this picture of their favorite beer, what they can do is they can tell the system that they want to improve the quality of the image by, for instance, tapping on it. So we have a plugin for Firefox that basically detects that the user taps on the image, and this tap is a hint that the fidelity has to be improved. So the mobile client basically talks to the adaptation proxy and tells it, give me a better version. So we send a better version. It's still adapted. It's still not the full fidelity version. But it's an improvement. Now, if this is not good enough, the user can ask for a further refinement, up to the point, obviously, where they get the full fidelity object. What's interesting is that the adaptation proxy actually monitors this exchange and learns from it, under the assumption that, well, if the user had to interact with the content, it means that the proxy didn't get it perfect, didn't get it right. And we're going to build a history based on what we call successful adaptations. And we deem success once the user basically doesn't ask for improvement. So either they're happy or they gave up. And we are going to assume that they are happy. Now, over a long number of users, hopefully, that will eventually be the case. All right. So what happens when user number 2 shows up, or actually user number 1 comes back? Well, if they happen to ask for the same image, well, now we have history. So we can actually use this history to do better. So we actually serve the image, the 20 kilobyte image, under the assumption that that will be fine. If user number 2 is not happy, he can again ask for an improvement, and that will help us keep building our history. All right. So how do we keep track of history? Basically, history of adaptation can be easily represented as a histogram. Not that the system is hardwired this way. But for illustration matters, let's assume that there are 10 fidelity levels. What we basically keep track is, which of these levels was actually desired by each of the users. So the different histograms that we have here represent, how many users wanted the image at a given fidelity level. So for instance, this is an example, and fidelity level is on the x-axis, where most users like the image at a very high level of fidelity. So this is an image that they were really interested in, presumably. This is an example where most of the users really didn't care that much about that image, or where a low fidelity version of the image actually did the trick. I mean, it was sufficient for accomplishing the task. So figuring out, how to adapt the image in these two cases where the history is very homogeneous is very simple. I mean, you basically just, figure out what's the mode or the average, and you just apply that. Well, as it turns out, life is not as simple as that. And there are many situations where the history is dirty. And the reason for this is roughly because there are many, many web pages that are actually used for multiple purposes. And where the purpose may actually affect the way the content should be adapted. And this is an example of that. We have, let's say, a group of users that are more than happy with the image at low fidelity, but there is also another group of users that really want the image at a much higher fidelity. So what do you do? If you serve the image at high fidelity, you're going to be wasting bandwidth for this, for the users that want the low fidelity one. If you serve the image at low fidelity, you're going to force those users that want high fidelity to interact with the system. So they're going to have to basically put more effort into it. And the total time that it takes them to accomplish the task will actually go up. So the question is, well, what should we do? And what we're trying to do here is, in some sense, we're trading off user involvement with bandwidth when we are transferring, I guess, when we're doing fidelity adaptation. So optimizing each one of these two is trivial. So let's say that I want to maximize user involvement. Or actually, it should say minimize user involvement, I'm sorry. So I don't want, I want to limit, the number of times that the user actually has to tap. Well, that's very easy. I just, provide them, a highest level of fidelity, and we're done. And the only problem is that that's actually costly. It's going to chew up a lot of bandwidth. And in all likelihood, if you happen to be using limited network, it's going to result in very low, slow downloads. On the other hand, if what I want to do is save the user money, it's also very easy to do. I just give you, the lowest fidelity. But the problem is that then the users are going to have to explicitly ask for refinements. And in total, if we look at, well, what's what we really want to do? What we really want to do is we want to optimize what we call fulfillment time, which is a metric of how long it takes you to get your job done. Get the page in a state where it's good enough for the task that you are performing. And this is really a trade-off between, it's a balance between how much content I download and how many times you have to interact with the content to improve it. So ideally, what you want to do is, download as little content as possible without forcing any interactions. That, of course, is unfortunately impossible because we don't know a priori exactly what the user will want. So instead, what we have is we developed what we call a personalized adaptation schedule, which is a policy that basically looks at the history of the adaptation, the amount of bandwidth that is currently available, and how long it takes users to interact. And based on that, builds a strategy, an optimal strategy for downloading the content. So it's basically saying, well, to bring an object to the fidelity the user will eventually want, there are actually two elements that I have to take into account. The fact that the more content I download, that chews up basically on the time, and every time the user interacts, that chews up a couple of seconds as well. So the total time will be download time plus interaction time. And what we want to do is we want to optimize that. So what we do is we have a program that basically does dynamic programming and looks at the history and figures out what is the best strategy, roughly, what's the first fidelity that, if I give you that fidelity, it's more likely that, that's the one you're going to be happy. Otherwise, if you interact once, it's going to jump to the next more likely fidelity. And over a large number of users, it's optimal. So how did we evaluate this policy? Well, we brought participants into our lab, and we asked them to use a PDA over a CDMA 1X network to download content and to perform tasks. Now, the PDA was communicating with our adaptation proxy, which was downgrading the fidelity of images. We turned prediction off, because what we wanted to do was get a sense of what were the fidelities that people really wanted. Okay, so it's sort of in learning mode. And we basically ask users to browse over a couple of sites. I'm going to present results for 2. And we gave them specific tasks to perform over those sites. And what they had to do is they had to tap on the images to raise their fidelity until they were good enough to perform certain tasks. What we then do is we get all these traces and we feed them to a simulator. And we look at how well different adaptation policies manage to match the ultimate fidelities requested by the users. So obviously, the best you can do is an oracle that basically guesses what the user will want, and that will give you the best fulfillment time that you can expect. So let me show you some results of this experiment. There are 2 graphs. They're for 2 different sites. One where basically all the users are performing the same tasks, so the history is homogeneous. And another one where actually users are performing different tasks. So we have, I believe, 3 different tasks. So the history is dirty. So let's see what we have. On the x-axis, we have 3 different policies. On the y-axis, we have time in seconds. So the first bar shows how long it takes you to finish the task if there is no adaptations, no transcoding whatsoever. And we see that that takes about 60 seconds. We then see that if we do, Oracle, which basically guesses, we know exactly what the users want. If we just serve them, that fidelity, this is, how long it takes to do the task. So there's basically significant savings. You go from 60 seconds to 20 seconds. That obviously is, the ideal. We obviously won't get as well as that. We then see that the simple policy that looks at the history and calculates a mean and serves that fidelity level gets, in this particular case, actually fairly close to the optimal. And our policy that looks at both interaction time as well as history and bandwidth, achieves similar performance. So this means that when the users are performing only one task, just a very simple policy that does mean on history does fairly well. On the other hand, when the history is dirty, which is what we are seeing here, that's actually not the case. If, again, so this is, unadapted, and this is mean, if you do the wrong adaptation, if you're just considering, history, but not the cost of interaction, which is what mean does, as it turns out, you can end up in a situation where, in fact, the total time to complete the task is actually higher. Why? Because you're downloading. Yes, you save a bit on the downloading, but then the users actually have to interact. So any savings on the time that basically you got from reducing the amount of content that you got, you lose because the users actually have to tap and have to interact, have to ask for improvements. On the other hand, we see that PASS can actually adapt to this situation and performs much, much better and really approaches the performance of the Oracle policy. We're within just a few percentages of the Oracle policy. And the reason is because, well, this policy gets an optimal schedule, an optimal strategy for roughly a set of fidelities that is going to jump through to get based on the history and based on how expensive it is to interact. Another example of how this strategy works and how it actually adapts to variations in the instantaneous bandwidth is what we have here. So we have the same, this is experiment I just presented in the last slide. So again, multiple tasks. This is when you're downloading over 1x bandwidth, which is about 90 kilobits per second. This is what we saw. At the time, we didn't have 3G in Canada, so what we did here is we sort of simulated the equivalent of 3G, and really is DSL 400 kilobits per second, which is actually what you get with EVDO, or I think Edge is in fact actually a little bit lower than that. And what we see is that obviously the times go down. The unadapted time obviously goes down because you have a faster network. What's interesting is that if you have your policy that just looks at history and it's oblivious of the immediate bandwidth that the user is getting, in fact, situation becomes much worse because the user is still required to interact quite a bit. So you actually end up hurting the user more than helping him. On the other hand, because PASS takes into account both how long it's going to take me to download stuff as much as how long it takes the user to actually correct the wrong decision, it becomes much more aggressive. And in effect, still does adaptation, but not as much, because it knows that if it gets it wrong, there is going to be a higher penalty percentage-wise. And because of that, it's able to better adapt itself to the situation where we have a better network. It still does better than no adaptation. And it definitely does much, much better than an approach that is oblivious to the bandwidth that the user sees. And this is actually quite important because even with 3G today, what we see with wireless networks is that the bandwidth changes quite a bit depending on where you are. And it can change very momentarily, especially if, like, let's say you're riding on a car or moving. So you may think that 3G basically fixes with 3G we won't need adaptation. Yeah, that's true as long as you actually happen to have a good connection. But in reality, over the course of the day, your connectivity changes, and as such, it would be nice if the underlying system realized this and adapted itself. All right. So I'm just going to quickly skip over the next few slides, and hopefully we'll get a few questions. So this is all nice and good, but we figured that we could actually improve it even better. We could do one more improvement by leveraging the fact that many websites actually involve many tasks on a website involve many different objects. So the question is, well, can we actually find correlations in the adaptation requirements of different objects so that you don't have to improve each individual object? In other words, if I figure out that the two images both either have to show in low fidelity or high fidelity, if we improve one of them, can I basically take that into account and automatically improve the fidelity of the other image? And when does this happen? This is one example of the Apple Store. And this is an actual screenshot of the Apple Store. And let's say that this is a user that is interested in buying an iPod. Well, if that's the case, they care about the top images, but they don't care about the bottom images. Okay? So if the system basically presented them, everything, at low fidelity, and if I somehow figure out that the user, let's say, taps on the iPhone, they eventually will tap on every single image because they want to see all of them at high fidelity, maybe I can actually leverage that. And the moment they tap on the iPhone, I basically improve the fidelity of all the images. But I don't do so for the images that they don't care about. So this is effectively a classification problem in some sense. We know that the content supports different usages. And when the user shows up, we don't necessarily know what they are going to do with the content. So what we are going to do is that we're going to probe the user. We're going to sometimes force them to give us some feedback. And we're going to use that feedback to classify them, to sort of figure out what is that they're trying to do. And based on that, decide, okay, if we figure out that this content is accessed for 3 different tasks, and each of the tasks requires images at certain fidelities, we figure out which one of those tasks they want, and based on that, we give them what they want. So let me show you how this works, more than the performance results. So basically, we have an example here where we have, let's say, a web page that has 4 images. And we somehow figure out that there are actually 3 tasks that are supported by this website. And each of these tables represents a task. And what we have here is, for each of the images, we see what is the average fidelity that people doing task 1 people doing task 2 people doing task 3 And we also know the minimum and the maximum fidelity that people doing those tasks want. And this is based on basically a k-means algorithm. It's just clustering. So what we want, when the a new user shows up, we don't really know if you think of each of these tables as basically a sub-community. We don't know, to what grouping the user belongs. So what we want to do is we want to elicit some feedback from them to drop as many groupings as fast as we can so that we can reliably say, well, this is the group that they belong to, so that we can better adapt the content. So in this case, what we do first, and assuming this is magically, let's say that this is what the user will want. So that's the targets that we're. Now, what the system, how does it adapt? Well, first, we don't know anything about the user. So what we do is we actually figure out what's of all the groups, which one is the lowest maximum fidelity that they want. And that's what we provide. Let's assume then that the user actually sees this content and basically tells us that the first image is actually too low a fidelity and raises the fidelity. Well, now we have one more bit of information. We know that maximum fidelity 4 for image 1 is not good enough, which basically means that the user cannot belong to this subgrouping. So we can just drop it. And we recalculate our predictions. So again, we take the maximum, the smallest maximum, which in this case basically means that image 2 is, goes to 9, 3 goes to 6, and 4 goes to 1. Well, the user interacts again, in this case, let's say, with image 3 and tells us, well, 6 is not good enough, which basically tells us that they don't belong to this other community. And at that point, we can automatically raise the fidelity of, we have identified them, we have classified them, and we can raise the fidelity. And this works very well. What you're seeing here are measurements of basically how many groupings. So we take the data and we basically do clustering into how many clusters. This is how many interactions are needed to complete the task, and that's how much bandwidth. And the policy I just showed you is this one, the blue one. And what you can see is that we are able to identify a nice sweet spot where basically we can complete the task with very few interactions and consuming very little bandwidth. So in summary, the second part of the talk that I presented is an approach that learns how to adapt content by monitoring the feedback it gets by letting users fix wrong adaptation predictions made by the system. I showed you how that can be leveraged across users, and how in fact we can actually correlate the adaptation requirements of different images so that we can automatically classify users and again reduce the amount of input that the user has to put in order to adapt all images or all content in a website. That URL over there, we don't have a fully working Eureka prototype, but that URL over there has pointers to all the papers we've published on this project and much more details. So I'll spend maybe 1 minute just talking about other work that my group is doing. We've done a lot of work on accurate techniques for indoor localization. So GPS is wonderful, and I used it to get here, and I'm sure you all use it pretty much every day. But the moment you step indoors, it stops working. Actually, the moment you don't have line of sight to 4 satellites, it stops working well. And in reality, people actually have done studies and have figured out that most people, in fact, spend over 90% of their time indoors. So in the places where we spend most of our time, GPS doesn't work. And wouldn't it be great if we had a localization technology that also worked indoors? And that's one interesting problem that we've been looking at. And the approach that we've taken is one where what we do is we leverage the existing cell towers that are deployed for communication. We leverage them for localization. We don't do triangulation, which is what the towers already do. Instead, what we do is we do an approach that's based on surveying. So if I want to localize people, let's say in this office, what I do is I walk around and I collect measurements of radio towers that I can hear. And each measurement includes the identities of the towers I can hear and the signal strength or the phase delay, depending on whether you're using CDMA or GSM. And I build a database with those measurements. And later on, when I want to localize someone, well, they take a measurement. And in my database, I look for a measurement that is similar. And then I do some interpolation. And this actually works fairly well. You can localize somebody within 3 to 5 meters indoors. And you can actually, for a tall building, you can actually tell which floor they are, which is critical for emergency response if you think about it. When you call 911 today from your cell phone, if you happen to be indoors, Bell and Rogers, they can't really tell where you are. In many cases, basically, they know where you are within about a kilometer radius, which if you're having a heart attack, that's actually pretty bad. On the other hand, if they knew what floor in the building you were, well, at least they can dispatch emergency personnel that then can canvass that part of the floor and look for you. We do another work where we leverage similar techniques to allow devices to pair securely. So wireless communication is great because there are no, basically you can just go anywhere and use it. The other problem is, the problem that it has is that you don't know, since you can't see wireless communication, there is no cable, you can't have any certainty about who you're communicating with. So this project is developing techniques that give you some assurances that your devices are actually talking to devices that are close, as opposed to attackers that may be using powerful directional antennas and may be very far away. And finally, our newest project, and I'll be very happy to talk to people about this, tries to make the life of social users in mobile environments better by automatically adapting the behavior of web applications to the context of the user, and specifically to who's around me. As an example of that, if you run into somebody and you want to schedule a meeting with them, when you bring your calendar up on your mobile device, it automatically figures out who's around you and adapts your calendar to show available entries of the people that are around you and things like that. And again, I'll sorry for being that cryptic, but I'll be happy to give you much more details about that project. So finally, although I sort of presented this work as if it was all my own doing, in reality, nothing could be farther from the truth. I'm just the advisor. In reality, all of the hard work and sweat that went into making this project a reality really goes to my very talented students and other faculty members with whom I worked, and those are some of their names. My email is there, as well as my website, and feel free to send me email if you have questions. And I'll be more than happy to take your questions. And thanks for listening for this presentation. Yes.
I have 2 questions.
Of course.
First, what did Milton do to get 2 mentions of acknowledgements?
Oh, that's it's his evil twin.
Yeah. Probably more importantly, is on the internal localization.
Yes.
What do you need to do on the device to collect them?
Let me just repeat the question. So on the internal localization, what do you need to do to actually localize people on the device itself? Well, you need access to We've actually played both with CDMA and GSM. For our GSM prototypes, you need access to signal strength information. And this information is available to the phone that the phone uses us to do a handoff. It's typically not provided to the application. So what you typically have to do is you have to hack into the phone and get access to it. We've actually done so with some models of GSM phones. But our hope is that in the future, phone manufacturers will see the value of this information and will actually make it available. I mean, it's there. They just choose not to bring it up. For CDMA, it turns out CDMA networks are much more dynamic than GSM networks. The size of the cell changes over time, and that affects the fingerprinting. So if your fingerprinting is based on signal strength, it just doesn't work for CDMA. On the other hand, CDMA towers are very tightly synchronized, which means that you can actually get very reliable timing measurements. And you can use the time of flight to do fingerprinting. So in that case, what you need is what we call a PN offset, which is really a fancy way of saying a measurement of time of flight, which is also available to the phone. And again, but it's buried deep down in the OS.
And you need to send that information to a centralized database or something?
So whether you need to send that information to a centralized database is a matter of implementation. So if, on current phones, it's easy to get a phone now with, an SD card, and you can, load on that thing several gigabytes. So you could presumably have a very large, database, fingerprint database on the phone itself and do the localization on the phone itself. Alternatively, what you could do is you could, upload the fingerprint up.
But where do you get the data on that if you load it to an SD card? The data you still need to get it from users, basically.
Somebody has to do the surveying, for sure. Yeah, I mean, that's the problem with this approach, that somebody has to survey the environment and collect the fingerprints. People, and us included, have looked at alternatives where we use, let's say, ray tracing to try to, given an environment and roughly where the large obstacles are and the radio sources, we try to pre-compute fingerprints. And we've done other approaches where what we do is we assume that we have a small number of devices where we know their local, their position, and we use the fingerprints to estimate relative distances. And that lets you do localization not with accuracies that fingerprinting, but better than what you do now without having to serve an environment. But yeah, there is no magic. And somebody.
Well, I was thinking maybe you have many people who send this information, and they also have their GPS information, which is very noisy. But maybe if you get many people, eventually you can localize them better and
Absolutely.
bootstrap one data set over the other.
Yeah, absolutely. You can do that. And in fact, actually, there are companies that are already doing that for Wi-Fi data. So if you have a smartphone with GPS and Wi-Fi, you can download this piece of software, and what it will do is once in a while it basically do Wi-Fi discoveries, and it tags them with GPS data and it uploads it. And yes, they have algorithms that basically reason, because you have noise there, and obviously people can misreport. So yeah, absolutely. There are different ways in which you can build this database.
Have you done any usability on the users modifying the page? Like, I mean, I understand that once I've modified the page and someone else looks at it and they see my modifications, they may get a benefit. But how easily do the users actually understand the UI in your prototype for modifying the page?
In the first project.
Yes, sorry.
Sure. We did some limited usability studies. So the modifications we actually tried were performed by non-technical users. These are, I guess, university students. They were not necessarily in computer science. Actually, most of them were not in computer science. We basically gave them about a 5-minute session where we describe how the prototype works, and they were able to figure how to use it. So the prototype is very easy to use. There is no coding involved. It's basically to adapt the page. All that you need to do is tap on a given item that you want. A menu shows up, and then you have to tell it whether you want to resize, move, crop, delete, and things like that. So we are fairly confident that normal users non-technical users can actually use it. We haven't done long-term user study where we actually give devices to people and we tell them, go and play with this for 2 months and let us know, what you think 2 months from now. That part we haven't done. So we haven't done a longitudinal study in that sense.
So I guess I should play with your prototype, but is there a modality to it? Like there's a mode where I'm modifying the content and a mode where I'm browsing?
Yes.
When I tap, normally I'm expecting to follow a link. I'm not expecting to modify.
Oh, absolutely. I'm sorry. I should have started by that. There is a top-level menu item that you basically, or a button that you click on it, and you go into basically editing mode, and you come in and out of it. Yes. Yeah. Otherwise, it would be very confusing. Sorry. Should have started by that. Thanks for that clarification.
Well, what are can you give us a set or the top 3 or 5 transformations that users do? Like first this block, then that, or this one above that?
So we have, for the first project, for PageTailor, so delete, resize both images and text, and move, roughly. Those are the 3 things. And, it's very simple but surprisingly powerful.
It's not hide or eliminate or delete?
Well, it's really hide. Other than, it is hide, really. The item is still there. Because if you completely delete it and there is JavaScript, which in many modern pages, there is tons of JavaScript, it just breaks.
Right, but from a user's point of view, delete and hide are probably the same.
Yeah. They can undo. There is also a button there that basically says, undo all modifications, and it basically brings the page to its original state.
And so I'm not sure you have enough data, but if you had to guess, if you had 5,000 user modifications of Amazon's CD site when you looked at it, how many clusters are there? Are there like 3,000 or are there 10?
I would think it's a small number. If I have to guess, I would think it's a small number, which is really the motivation for the second part of the talk. So I would think it's a small number. If you look at, if you can somehow batch the modifications, because let's say, which in our case, actually, when we say resize, it's not freeform resize. It's basically jumping between, specific sizes. So, yeah, I would expect to see a small number of modifications. 10 is probably even an upper limit. My guess is, it's probably an 80-20 rule, right? Most of the users will probably be happy with, one specific, and then you'll have 2 or 3 more. But this is pure speculation. I don't have the data to back it.